Hello everybody, welcome to the presentation of ULab Studio for Delphi. My name is Janez Makovsek. I will be presenting this product for our company, Due Research. First, to give you an overview of the development of the product, the first version was released in July 2001. Next one was released in 2004 and so on until last December 2014. Each time on introducing some new major feature. In 2004, it was the first time that we introduced standardized tests for all the functions. In 2007, we added operator overloading in debugger visualizers. In 2010, we introduced support for integer math and OpenCL library. And in December 2004, we came out with support for full support for FireMonkey and for Android, and ability to compile the library as a 100% full Pascal source. The audience of this presentation, the expected audience is for independent software vendors and in-house development for universities and research institutes, and of course for students. The license for the products that I will be presenting is a commercial license. It is required if you want to deploy an application built with the product, but it is free for students when being used from Delphi IDE. This, for example, is comparative, or let's say better than what some of the competitive products performing the same thing require. And there are no next screens while working with the trial version from IDE. The platform supported covered Win32, Win64, Android, iOS, and OS X are planned by the end of June this year, but Android, Win32, and Win64, both VCL and FireMonkey, are already fully functional and tested. Common feature to the library. Library is a scientific math library. It has a vector matrix coding style. It features best performance when using Intel CPUs with support for AVX instruction set. It has a very good integration with the debugger and features hundreds of functions and components for in the fields of mathematics, statistics, and digital signal processing. On our first feature, we can look at the complex numbers, how it makes it easier to treat complex numbers in Delphi. The support for complex numbers is built into the library throughout every layer of the structure. Every function which is called can optionally be executed as a function which takes real parameters and a function which takes complex parameters. And here we see in the first line that we can assign a string to a variable of type complex, and there will be automatic conversion from complex from string to a number. Then there is, of course, standard operating overloading for complex numbers and a complete comprehensive set of functions to handle complex numbers. And finally, of course, there are functions to control formatting of the complex numbers back to string. This is just one example here, but the support is actually comprehensive, the same as there is available for real numbers in Delphi. Now we move to the first major feature of the product. As we can see here, we can declare variable of type vector. To initialize this variable, we declare an array. This is a fairly new syntax, which was introduced with Delphi XE7. What happens in this first line is that this expression on the right side is first converted to dynamic array, and this dynamic array is then assigned to an object of type vector. In this case, we have a copy operation. In the second line, we can see that the object of type vector has full support for operator overloading. Now, this vector could hold real numbers or complex numbers. And of course, in when mixing variables which are real and complex, this is also possible to be done in expressions. Finally, we have a comprehensive support for math functions, also for vectors. Now here we have one fairly common functions, which is exp10, but there are dozens of functions like support for FFT, support for summation, support for product of elements, basically all the standard functions that you would expect from that you would like to perform a vector. Here we have an example below that it's possible to pass a vector variable to various functions like product and sum. Then we move to matrix type. The matrix type, in this case, again, perhaps I forgot to mention on the first slide, when you declare a matrix or vector object, as you can see, there is nowhere you are creating anything, and you are also not freeing anything. So memory management is completely automatic. Here we have an example. Again, XE7 is required for this syntax. If you want to perform matrix multiplication, not element by element multiplication, then we call a function. But if we want to multiply individual elements, then we would use the standard multiply operator, as we have here in BM times BM. The matrix object has, again, comprehensive support for math functions. One is for eigenvalues, for example, or for solution of linear systems. And there are some 20 or 30 overloads for functions, for example, for eigenvalues, and multiple overloads for linear system solvers of various flavors. Real parameters, for complex parameters, for symmetric matrices, for general matrices. Just about the whole set of course, also the generalized eigenvalues and some special functions. Here we move to the question: how do we handle individual elements within the vector and matrix objects? And we can see that the syntax is the same as for the dynamic arrays. The important thing to mention here is that not only the syntax is the same, but the performance is also a match. So there is no penalty here for the fact that these are not simple arrays, and this feature was introduced with Delphi XE6, where the performance of inlining of functions was significantly improved. Here we also have one example how to copy a dynamic array to vector, how to set the vector to 0, because sizing will not set the vector to 0. This is can save quite some memory bandwidth, because if the vector will be overwritten, then it's no purpose to first set it to 0. Here we have one interesting assignment, because assigning a dynamic array to a vector will actually perform a deep copy. We have the option to use operator overloading, functions, or methods. So nearly all the methods which you see here, which are being called on the vector, are also available as functions. Yes, how to, for example, the for loop is self-explanatory. Now we move to the next type. This is the support for integer math. We have a type of vector int. In the same way, we just declare it. We don't need to create anything. We don't need to destroy anything. All the memory, everything is handled for us. Now, you might think, well, if behind all this syntax there is hundreds of lines of code being creating and destroying objects or whatever, that is not the case. The handling of memory, the creating of objects is very smart, and these expressions which you see here on the line on the display, and what we have seen on the previous slides, there is not a single line on which an object create is called. A constructor is executed. So all this, what you see here, is done without object constructor and without calling object destructor. And there is no memory which is being freed and no memory which is being allocated. This may sound like unusual or maybe crazy, but this is very important when we are trying to thread our code, when we are trying to achieve maximum performance, and then we want to have fixed memory addresses and no sharing of the common resource, which would require synchronization between threads. Now we come to code vectorization. So what is the main benefit of code vectorization? The main benefit is the speed. That is the first benefit. And the second benefit is readability of the code. Now, changing for loops into matrix vector operations, that is not a trivial task. And that is something which is absolutely required and cannot be avoided if we want to have the advantage of our code running at impressive speeds. If we do our thing right, now if we vectorize correctly, and then if we also multithread correctly, we can take our Delphi code to our performance, increase the performance of our Delphi code by about 100 times, and this is not something which is exceptional. And this is only on a 4-core CPU, making wise use of the hardware architecture. Now, the library has a comprehensive support for efficient multithreading. Allocation and deallocation or sizing of vector matrix and vector int is not blocking for threads. It even works hard to avoid the lock instruction. As you know, lock instruction is required if you would like to write or to access the same variable in the main memory, and you would like to have this value synchronized between multiple threads without getting corrupted. So we are not that we are only avoiding critical sections, event objects, and various synchronization objects for inter-process or the inter-thread synchronization. Even on the integer, on the, let's say, on the single variable level, every effort has been made to minimize the number of conflicts between individual threads, so that we get to have full parallel performance as much as possible. All functions accepting vector metrics and vectoring variables are not blocking the threads, so they can be executed completely in parallel without virtually any blocking. Then we have a lot of algorithms which are already internally threaded. The most basic algorithms like this are matrix multiplication, and then you go to various more complex matrix operations like eigenvalues computation or linear system solvers, and finally to FFT algorithms. There is a fair amount of code patterns and examples for multithreading. Multithreading is available with the library. And you get to have a flat 4x speed up for 4 CPU cores when the threading is done properly. The idea to multithread code without first applying code vectorization, we can only say that this is a waste of electricity, because the gain which comes from code vectorization is about 20 times, as we have seen on the previous slide, and the gain that comes from the using 4 times more electricity using 4 cores is only 4. Now, when you debug your code, what you see here is the local variables window. And when the debugger detects either vector or matrix or integer vector, it will show you the content of that object. First, it will show you what is the size, and then what is displayed inside. And also, you have the option to press the hourglass to get another type of display. This is another type of display you can see here at the bottom. On one side, you can see a standard grid display, which is configurable. You can specify number of places, delimiter, number formatting. It will display real and complex numbers and so on. And on the right side, we can see that if we press a button, we also get to see a chart of the data which is stored in the object. Finally, what we have here on the right side, on the left side, is an expression at the bottom. This expression means that we can type in matrix vector operation and have the result immediately updated in the grid. So if the variable here, which is a BM, is passed to a function, and that function is here below, y equals x times 2, then the BM will be multiplied by 2 and displayed in the grid below. Now, these expressions here below can be very complex, as we will see later on. Yes, to give you some idea of usability of this user interface, you can have all these charts and grid this updated live while you are stepping through the code. So each time you press F8, 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 all these charts, multiple charts, is here we have only 2, but you can have any number are displayed, and especially for some, let's say, more complex optimization algorithms, a debugger which does not have such display of variables, basically without such a tool, some algorithms you simply cannot debug, or it would take disproportionately long time and effort. Yes, now we have an extremely short example of how we can run OpenCL kernels from Delphi. As you can see, there is now one new type declared, which is called CL vector. This CL vector can again hold real or complex numbers, and they can be single precision or double precision, depending on how you initialize the engine. Here we're gonna we have one other type declared, which is AV. This type has the content of this AV vector resides in the CPU memory, and the content of the AV vectors reside on the GPU memory. So when we call copy, we are actually copying memory from CPU to GPU, and using expression overloading, overloaded expressions, we can execute code on the GPU, and finally, when the code is finished, we call the copy to get the result back from the GPU to the CPU. There are several things here which might cause eyebrows to raise, and then questions: what does here happen? And does this really work? Does this really have some benefit? Now, if you debug this code and you move your mouse over the variables A or B, you will get to see on every line what is the content of the variable inside of the GPU memory. So this is already the first simplification and a great help, because you get to have the same kind of benefits which you are used to when debugging Delphi code on the CPU, you get to have when debugging code on the GPU. What we don't see here on this example are two lines where we initialize the OpenCL driver. The first line of this initialization tells the OpenCL library that on which device we want to run. And the second line tells which kernels we want to load. Do we want to load single precision, double precision, and depending on the availability or capability, if we want to load kernels both for the CPU and for the GPU. And after we have executed these two lines, we are ready for running OpenCL kernels. We can run pre-prepared OpenCL kernels, like you can see on this slide. The OpenCL kernels, in this case, in case of these expressions, they will build a list of kernels, which will be, this list will be passed to the GPU, and the GPU will work its way through that list, and when that list will finish, there is a command here, copy to, which will copy the result back to the CPU. The point is that all these calls here, like log 10 plus 2a, these are non-blocking calls. And the copy to, that is a blocking call. So the result will not be available until you copy data back to the CPU. If you debug, the debugger will make that data available. But if you don't debug, if you don't have this running in the debugger, the actual variables will not have data until the copy to line. Of course, this what is in between. This can be a lot of code. And there are two parameters here which make this economy work. First, you can have a for loop, which will submit a large set of GPU kernels to the GPU. And the second is that you can have the size of individual variable can be very, the bigger the better. For example, like 10 megabytes or 100 megabytes. And these two parameters, the bigger the number of kernels and the bigger the size of the variables, that make, and of course the third one is the number of lines of the code. This can be also immediately increased if you have a for loop in your algorithm. This defines if the computation on the GPU will be faster than the one on the CPU. Now, this type of expressions, as we see here, this is far from something which you would call general computing, but it does get you to be very, very close to writing only that specific part or only that custom kernel which you need in your application to get the performance that you want. So if you want to write a custom kernel, you have everything solved. You have the selection of the device is done for you. The copying of data to the GPU is done for you. All the basic operations like we see here are done for you. The only thing you need to do is to write your kernel, which is maybe like 10 or 20 lines of code in OpenCL-C, C or whatever the driver supports. And we had some customers which were very, very successful and surprised that you can write a few lines in Delphi and get a full-blown OpenCL kernel working on a real world, in a real world example, and get very good results. Very good results. We are talking about 500 times faster than what Delphi might manage, and let's say 10 times faster than what our library could manage on the CPU. One part of our library covers also ability to run simple scripts or simple expressions, so to speak. It's an expression evaluator. There are many math expression evaluators which are free and you can find on the internet. But usually what is common to them is the moment you get to have more syntax or more features of the syntax, that moment is when the performance starts to drop. And in our case is we have expression parser or expression evaluator, which gets to be pretty darn complex, but the performance will match or exceed most, or I wouldn't want to say all, free simple expression evaluators. That is something which is special. The other thing is you get to have support for complex numbers. You get to have support for vectors, for matrices. Many of the operators that you might be familiar with from the school or from doing some work with MATLAB or Scilab or something similar, like transposing the matrix or like specifying the range of indices. For example, 0, column 2 means that we want elements at indices 0, 1, and 2 from the vector x to be considered in the next operation. And if we have like 2 colon minus 1 colon 0 means that we want them in reverse order. And if we have 10 colon 15 means that we want a vector which contains elements 10, 11, 12, 13, 14, and 15. We can play with this in various ways. For example, M here is a matrix, and we say we will consider elements inside of this matrix, and this is 0, 1, and 2, and we will assign an array to that to those indices. Again, this is done in an extremely efficient manner. So if the indices are large, and even if they're not large, the amount of code that here actually gets to be executed is very, very thin. And the overhead, I'm talking about the overhead. And the performance results for this, for all the feedback that we had over the years from the customers, are they seem to say it's second to none. It's top of the range. You can also do stuff like, for example, linear system solvers or least square solutions and similar. And of course, you can write and add your own custom functions. So a short overview of available function domains. So we have linear algebra for real and complex numbers. Then we have optimization methods like simplex, Marquards, various other methods, support for sparse matrices, support for eigenvalues of sparse matrices, linear system solvers for sparse matrices, multiplication, mixing of sparse and dense matrices in the expressions, then random generators. These are really professional random generators. So if you have a quite special case where you want to have a really high quality random generators, you can use our library. Standard special functions, support for integration, differentiation, polynomis. Polynomis is like finding zeros and poles and multiplying polynomis together and so on. And there is also TeeChart support functions and series. Yes, the C++ builder is supported. It has a specialized layer written in C++, so that you get to have all the flavors that you have seen in Delphi, plus all the good stuff from C++, and you can run this in 32-bit and 64-bit C++ compiler. Finally, the whole library has two add-on packages. One is digital signal processing library, which is for processing audio, vibration, application in medicine and industrial engineering, and the second one is statistics, which applies in engineering and financial applications. With the introduction of the Delphi supporting iPhone, Delphi supporting Android, Internet of Things, and so on, the target audience, of course, greatly increased for our product, because you can take full-size desktop application, which is built with our products, specify the target to be Android tablet, build and deploy to the tablet, just like that. And even if that, I'm talking about a tablet, because in this case you don't even have to adapt the user interface. Even the user interface can stay the same. If you're willing to forget about the user interface, you can deploy the whole library, the whole big application to your, I don't know, eyeglasses or your watch or your phone or whatever you're using, which is, of course, has to be supported by the Delphi as a target. There we have multiple demo applications, one for math library, one for signal processing, one for statistics library, and each demo has a large array of examples featuring all the different aspects of the libraries, which you can download them from our website. Download contains both VCL and FireMonkey variants of the same demo. Yes, and as I said before, FireMonkey version runs on Android tablets the same as on Windows desktop, which means you get a one-to-one portability. As soon as you are able to run Android on your device, you can take your Windows desktop size X application and simply dump the whole thing on your phone or your watch. And finally, I have to say credits and thanks to David Indersimon, Mark Cantu, and Embarcadero Delphi team. Many of the code syntax features present in our products have only been made possible by Delphi compiler team, which implemented many of our suggestions. So the courtesy and the glory and everything that is good goes to the people which were so kind that have listened to us and have helped us to make our product a success. So,
Alpha's asking, is there support for nonlinear regression analysis like fitting y equals and a times x divided by b plus x?
Yes, of course. It's available in the statistics add-on.
Okay. All right. I had a couple of questions. Have you done any testing? You kept saying Delphi, but you've tested on C++ Builder as well. Is that right?
Yes, of course. We also have demo applications, which is nearly one-to-one comparable to Delphi, and it is running the same in the C++ Builder as it does in Delphi.
And then, as far as GPUs, do we care what the model of GPU it is, or the manufacturer, or is that under the?
As long as there is driver support, like standard driver support from the maker, which is like all the major makers supported. We have only three. One is Intel, the other one is AMD, and the third one is NVIDIA, and they all support OpenCL.
Okay, excellent. Yep. And I had one other question. Well, people might put other questions in. You mentioned that the that the iOS support is coming out. I guess it's next month sometime. Is that?
Yes.
How is the product licensed? If there's updates, what happens as far as purchasing and updates?
We offer our customers subscription.
Okay.
It means that once you buy the product, you get 1 year of subscription. During this subscription, you get updates to all the new versions of Delphi or C++ Builder or whatever you're using. After 1 year has expired, you can extend your subscription for the price of about 1/3 of the price of the new license.
Okay, excellent. And then you mentioned the add-ons. So the base product,
yes,
MtxVec.
Yes.
And then if I want the statistical part, I just add that on. Is that right? Is that how it works?
Yes. Then we have bundles also offered. So when you want to buy the products, you can select 1 or 2 add-ons, or you just buy the whole package, and the whole package, of course, is discounted even more.
Okay. And then as far as the trial is concerned, how does the trial work again? Is it stripped down? You said there was no nag screens, I think, right?
Yes, correct. There are no nag screens, but it won't work without running Delphi ID.
Okay, it runs an ID. Okay,
yes.
Sorry, I missed that part. I apologize for that. Okay, and if there are other questions, you can put them in now. Otherwise, any other last words, Janez? Oh, wait, Pat is saying, "Oh my gosh, I wish this was available when I was an electrical engineering student in the '70s."
It is like this that I wouldn't be doing this with Delphi if I wouldn't think that the Delphi is the best development system. And this is I have a lot of fun, a lot of joy working with this, and I can only say that I'm a Delphi guy.
No, so great. Thank you for the presentation, and thank you, everyone. This is really cool. The only thing I need to do now is fire up some of the functions and listen to the fan go on my computer as the GPU does a bunch of its work. That's always a fun thing. And for everyone, I put the link to the product page in the chat window as well. But it's just go to doresearch.com, DEWresearch.com. Pretty easy, and all the info is there. I have a couple questions, and then maybe others will chime in with questions. What are the types of developers that are using these libraries? Are they scientists and engineers or other types?
Well, I have to say that about 50% we have people from various universities, like people that are employed there. These are not students, but actually professors, assistant professors. And then we have another group of clients which are associated with process engineering in development, in, let's say, in vibrations, in mechanical engineering, and electrical engineering. And finally, there is also some. We have some users in defense sector.
Okay, and then can you give everyone?
Of course, there is also some financial. There's some large banks, and there's some oil companies, and so on.
And then, what can you tell without giving away your customer secrets? The types of applications they're building? Are they simulations, or are they data analysis, or different types?
Well, there is, for example, one common feature that many people are doing. Then that is regression, function regression. So you have a series, and you want to feed a function to that series. The purpose of feeding the function is either to be able to interpolate or extrapolate into the future. Interpolate means finding a more accurate value between 2 points, or finding a value what will happen in the future. For example, everybody that's working in the financial sector wants to know what will be the stock prices tomorrow.
Sure. I suppose actuaries, they always are calculating all sorts of things out for.
Yes, of course. And then they have maybe, I don't know, 10 different pointers to tell them where things will move.
Mm-hmm. So do you have any customers that are integrating 3D type things where they're doing calculations and then displaying them? Or is it more charts and graphs and things of the data?
There are certain customers which are doing finite element analysis. Finite element analysis is used in construction and in mechanical engineering, where you want to check the strain on the structure, and to make sure that you cut out all the red areas where the strain is so large that the structure would fail. That is a very simplified example, but the result of these calculations is then indeed a 3D chart.
Okay.
Although we don't actually do the 3D chart, but the math we require to produce it is done by our library.
And then MtxVec, that's the main, is that the main library, and then there's some add-on modules? Or?
Yes, correct. MtxVec, that's the matrix vector library. And the other two add-on products are built onto this. So they use the functions from the math library and all the good sides and all the good features.
Okay, great. Jim, I think you're there as well. I don't know if you have any questions for Janez. There aren't any in the queue right now, Janez. So, I mean, for me, this is all some of my past, dark past, way past, long before I came to Borland and Embarcadero. But
yes, I have seen that you have mentioned to be using Fortran in your school.
Well, it was the first language that I learned, and then I went to assembler and COBOL, PL1, and that's how far terribly back, but lots of math libraries, and more recently, exploring GPU computing. I know NVIDIA, for example,
Yes.
is a big proponent of giving you these Tesla boards with lots of GPUs that you can use not just for gaming, but for all sorts of analysis, signal processing, and so on. Yeah.
There is one, I think, the good thing about Fortran, because many of the, or let's say some of the features of Fortran which were good at the time, they have survived until today, and they're still used. For example, the most prominent is the use of MATLAB and Scilab, which use basically the same syntax. But they all grew out from Fortran, and they use many of the same concepts and even syntax, which was introduced in Fortran. So I think this is a testimony that how good things survive the test of time.
I think the classic library was, what was it, IMSL for Fortran?
Yes, that is still being sold today.
Okay.
It is, I believe it is, I'm not sure if Intel is still reselling this. I believe so. They have one package of which is rather expensive, and they include this library as a part of it.
Yeah. The great thing for everyone here is that you can use Delphi and C++ Builder and have the power of all these libraries. So check it out at doresearch.com.
I've had a number of people ask me if there were any Delphi libraries for doing vector math and complex numbers and working on GPU and stuff like that. So it's great to see you're making these libraries available to developers, because this is certainly something that is popular and that people are interested in doing.
Yes, well, thank you. We have been working on this since, as I said at the start, since 2001. And the thing about the development of the hardware is that you get to have your application run faster with every new CPU generation only if you are able to vectorize your code. Because if you follow how the instructions are added, you get to see, for example, from the generation 3 of Intel Core architecture to the generation 4, only the vectorized code received a boost of 2, and the rest was maybe 10%.
No, this is great stuff. It shows, for me, we do a lot of database things and GUI things and so on, but this shows what you can do when you want to do real engineering work, real scientific work, even if you're going to put like charts and whatever else or access databases along the way. There's a lot of people doing scientific and engineering programming in Delphi and C++ Builder, and this is a great set of libraries.
Yes, thank you very much, David.
Okay, all right, everybody, take care. Thank you very much for being with us.
Yes, bye.